The question says that a computer system implements a 40-bit virtual address, page size of 8 kilobyte and a 128 entry translation look aside buffer, which is also called TLB, organized into 32 sets, each having 4 ways. Assume that the TLB tag does not store any process ID. The minimum length of the TLB tag in bits is. Okay, so one thing that you need to know here is that whenever we talk about virtual address, a virtual address is specified, or it consists of two major fields, and those two fields are the page number and the page offset. Okay, so the two fields that would be present would be page number and the page offset. Alright, so here we are specified, or we are told that the virtual address is of 40 bit. So this entire value is of 40 bits in length, and we are also told that each page size is 8 kilobyte. So page size means that a single page would have 8 KB of addresses, or the total number of different addresses that can be present in a single page would be 2 raised to power 13. And how did I get 2 raised to power 13? See, 8 kilobyte is equivalent to 2 raised to power 13 bytes. Okay, and 2 raised to power 13 bytes are possible, or with using 13 bits we can represent a total of 2 raised to power 13 bytes, or 2 raised to power 13 different addresses. Okay, so what we can say here, that the page offset basically tells a single location within a particular page. So to tell a particular location in a single page, we need 13 bits. Therefore, the total number of bits that would be reserved for the page number field of the virtual address would be 40 minus 13, and this would come out to be 27. Alright, now what else you need to know, that when we talk of this particular page number field, in the presence of translation look aside buffer can further be divided into two fields. And what are those two fields? The two fields are TLB tag, that means translation look aside buffer tag, and the second part is TLB index. Okay, now you must be careful that there is a lot of information specified into this question, and some of this information is not actually needed. So this entire field is, the page number field is 27 bits, and we have to find the value or the length of the TLB tag in bits. So this is the value that we need to find, and to find this value we need to subtract the length of TLB index from 27. Since it is given that there are 32 sets each having 4 ways, therefore 32 can be represented as 2 raised to power 5. That means using 5 bits I can represent a total of 32 different sets. Therefore 5 bits are used to represent these TLB index field. And one thing to note here, that you do not have to take into consideration 4 ways that is specified here, or this value, that 32 sets each having 4 ways or 4 columns. Here this value is not needed, because we do only have to calculate TLB index, and TLB index basically talks about the sets, the number of sets that are specified. Since there are 32 sets, each in 32 set we have 4 ways, so to represent different sets we only need 5 bits. Therefore this tag field, TLB tag field, would be of 27 minus 5, which is equal to 22 bits. So the answer for this question is 22. This question is particularly important because you need to know that you don't have to subtract this value, or 4 is equal to 2 raised to power 2, and you do not have to subtract 2 from this 22 bits. Okay, because we only need 5 bits to represent the 32 sets which are actually represented by the TLB index field. Okay, now we'll switch to the second question. The second question says, a computer system implements 8 kilobyte pages and a 32-bit physical address space. Each page table entry contains a valid bit, dirty bit, 3 permission bits. If the maximum size of the page table of a process is 24 megabytes, then the length of the virtual address supported by the system is dash bits. Alright, so here it is given that you have a size of 8 kilobyte page. Okay, the size of each page is 8 kilobytes. So what does that mean? 8 KB pages means that each page represents a total of 2 raised to power 13 different addresses. Okay, and how did I get 2 raised to power 13? 1 KB is 2 raised to power 10 and 8 can be represented as 2 raised to power 3. So 2 raised to power 13 different addresses can be represented by a single page. Therefore, the number of bits required to represent the page offset would be 13 bits. So when I say page offset, you must remember that a physical address has two different fields. One is the frame number. A frame number corresponds to a particular page that it is mapping, and then it has the offset field, the page offset of the frame offset field. This particular division of the physical address is a total of 32 bits in length. Okay, so this is a physical address which is given to us to be of 32 bit, and we have calculated the length of the offset field to be 13. All right, so this field is 13 bits in total. Therefore, the frame number or the field that represents the frame number is equal to 32 minus 13 bits. All right, now remember this because this value would be used later on, and this will come out to be 19. Okay, now what else is specified to us? We are told that each page table entry contains 1 valid bit, 1 dirty bit, and 3 permission bits. So how is a page table entry actually diagrammatically represented? One page table entry consists of certain bits that are reserved to represent total number of pages. Here, frame number is equal to 19 bits. That means there are total possible frame numbers that are actually required to represent such a system would be 2 raised to power 19, because 19 bits can represent a total of 2 raised to power 19 frames. Alright, and that means we can map to each frame one page. That means 2 raised to power 19 pages. So if we have a page table entry, we would have something like this, that there is a page number of pages or the page number that we are mapping to, which would correspond to this frame number, which would be same in the number, in the size that is of the frame number. That means this page number field would also be of 13 bits. Okay, sorry, 19 bits. Then we have 1 permission bit, we have 1 valid bit, we have 1 dirty bit, and we have 3 permission bits. So this page number corresponds to the frame number field. That means there is a direct mapping between frame number and page numbers. Therefore 19 bits would represent this page number field, 1 bit for valid, 1 bit for dirty bit, and 3 permission bits. Therefore this total size of one page table entry would come out to be 24 bits. Alright, so what we have calculated till now, we have found out that the total number of frames or the bits required to represent the frame field in the physical address. Then we have calculated the size of one page table entry. Alright, now what is further specified in this question? We are given that the page table of a process can be maximum of 24 MB. Now you must remember that one page table has multiple pages, and the size of a page table can be calculated by multiplying the number of entries by the size of each entry. Okay, so what do I actually mean? That 24 MB is equivalent to the number of page table entries multiplied by the size of one entry. So I'll write down here the formula. The maximum page table size is equal to number of page table entries multiplied by the size of each entry, each page table entry. Okay, so here we know that maximum page table size is 24 MB. We do not know the number of page table entries, but we know that the size of each entry is 24 bits. This is one page table entry and each is of 24 bits. So 24 bits represent how many bytes? It represents 3 bytes because 1 byte is equal to 8 bits. Alright, so to calculate the number of page table entries, we would take this as 24 MB divided by, sorry, this represents 3 bytes. 24 divided by 8 is 3. This divided by 3 bytes, which is equal to number of page table entries. And what would be the value? Number of page table entries would come out to be 8 MB. Okay, 3. This comes out to be 8 MB. So this is the total number of page table entries. Now, why do we need the total number of page table entries? Since the total number of virtual addresses, that is what we have to calculate. The length of the virtual address supported by the system is dash bits. So we have to calculate the length of the virtual addresses supported. To find that, if we find out what are the total number of virtual addresses, we'll be able to tell the number of bits required to represent them. Because if there are a total of 2 raised to power n addresses, then n bits would be required to represent them. So what is the formula or the relation between page table entries and virtual addresses? We know that the total virtual addresses, okay, total number of virtual addresses is equal to the number of page table entries multiplied by the size of each page. Now, how did this formula happen, or why is this formula correct? So, see, whenever you have to find out the total number of virtual addresses, first you will find out how many pages exist, because virtual addresses exist within pages. So if there are n number of pages and each page consists of, suppose, 10 virtual addresses, so total number of virtual addresses would be number of pages multiplied by the number of addresses in each page. So n into 10, that is 10n. Okay, so here also number of page table entries with which indirectly tell the number of pages that exist. So it is equal to how many number of page table entries we have? We have 8 MB of page table entries. And what is the size of each page? The size of each page is given to us as 8 kilobytes. Okay, 8 kilobytes, and when we multiply them, 1 MB multiplied by 1 KB gives 1 GB, and 8 into 8 gives us 64. So this would come out to be 64 GB. Now 1 GB is equal to 2 raised to power 30 bits, and 64 can be represented as 2 raised to power 6. Therefore, this is equal to 2 raised to power 36 bits. Sorry, 2 raised to power 36. So total number of virtual addresses that are present are 2 raised to power 36. So the length of the virtual address field that would be required is 36. Because using 36 bits, we can represent a total of 2 raised to power 36 virtual addresses, and this is the answer. So this was a quite lengthy question. I would summarize this by saying that if we have to find the length of the total virtual addresses that are possible, we first need to find out the total number of virtual addresses. Sorry, if you have to find out the length of the virtual address field, we need to find the total number of virtual addresses, and total number of virtual addresses are calculated by this formula. So we need to know what is the number of page table entries and the size of each page. We are given the size of each page as 8 KB and number of page table entries. How can we calculate the number of page table entries? Number of page table entries can be calculated by this formula, which states that the maximum page table size is equal to number of page table entries multiplied by size of each page table entry. So this value is given to us as 24 MB, and size of each page table entry can be calculated like this, where a page table entry has one valid bit, one dirty bit and 3 permission bits apart from the page number field, and this page number field is calculated from the relation that is given between the physical address and the offset. Okay, so physical address consists of two fields, the total of 32 bits minus the offset length, which is 19, minus the offset length gives us the value of 19, which is equal to the frame number of bits required to represent the total number of frames, which is equal to number of bits required to represent this first field of a page table entry, and therefore a page table entry gives us a total of 24 bits. And that's how we have calculated the two questions and the answers of these two questions. So I hope you get a understanding of how things are working in both these questions. So if you have, the question is, consider a uniprocessor system executing three tasks T1, T2, T3, each of which is composed of an infinite sequence of jobs which arrive periodically at intervals of 3, 7 and 20 milliseconds respectively. The priority of each task is the inverse of its period, and the available tasks are scheduled in order of priority, with the highest priority task scheduled first. So each instance of T1, T2, T3 requires an execution time of 1, 2 and 4 milliseconds respectively. Given that all the tasks initially arrive at the beginning of first millisecond and task preemptions are allowed, the first instance of T3 completes its execution at the end of dash millisecond. So it's a numerical type of question in which you have to calculate, perform all those operations that you have given in the question and then fill in the blank. Okay, so important things to note in this question are that there are three tasks which will keep on arriving at particular intervals. Okay, so they are not always available. That means if I write down T1, T2 and T3, so the first instance of all these three is available at 1 millisecond. Okay, but after 1 millisecond they arrive at different intervals. Okay, so the T1 task arrives after 3 milliseconds. So 1 plus 3, 4 millisecond. It will, the next instance of T1 will arrive at 4 millisecond. Then T2 arrives after 7 millisecond. So after 1 millisecond, T2, the second instance of T2 would arrive at 8 millisecond, and T3 will arrive at 20 millisecond plus 1 millisecond. That means the second instance would arrive 20 millisecond later than the first instance. Okay, and so this will arrive at 21 millisecond. Okay, now continuing in this manner, the third instance of T1, T2, T3 would arrive at 4 plus 3, that means 7 millisecond, then 8 plus 7, which is equal to 15 millisecond, then T3 would arrive at 21 plus 20, which is 41 millisecond. Okay, and if you go on and continue in this manner, the fourth instance of T1 arrives at 10 millisecond, then here it arrives at 15 plus 7, which is 22 millisecond, and 41 plus 20, again 61 millisecond, and so on. Okay, so we have to find out that at what time the first instance of T3 completes. Now you are given that the priority of these three processes is different. Okay, so all of them are not of the same priority, since it is given that the priority is inversely proportional to the period. This is the period. Period means that at what or after what interval of time these jobs are repeating or the instances appear. So lowest period is of T1, so T1 would have the highest priority. Okay, so let me write down here in terms of priority. T1 would have the highest priority because it has the lowest period. Then the second highest priority will be of T2, and then T3 would have the lowest priority because it has the maximum period. Okay. Now, what does this mean? That if we have to preempt a particular process, it will be preempted in case a higher priority process arrives. Now, another thing that is specified to you in this question is the execution time. What does that say? That T1 takes 1 millisecond to complete, but T2 and T3 take more milliseconds, more amount of time to complete. And how much is that time? Let's see. T2 takes 2 milliseconds to complete, and T3 takes 4 milliseconds to complete. Alright, so using all this information, we'll find out how much time, or at the end of what time T3's first instance gets completed. Okay, now starting with the 0th time, since 0 to 1 no process is available, all the processes or the first instances of all these three processes become available at time instance 1. So at 0 to 1 nothing is available. At time 1 all of T1, T2 and T3 are available. That means the first instance of each of T1, T2 and T3 is available, but since T1 has the highest priority, we'll take up T1 and execute it. Now, how much time does one instance of T1 require to complete? It only requires 1 millisecond. So, at 2 millisecond, it is completed. Now, at 2 millisecond, we have, how many processes do we have? We have process T2 and we have task T3. Okay. So T2 has higher priority. So we'll schedule T2 here, the first instance of T2 here. And since T2 requires 2 milliseconds to complete, therefore 2 to 3 and another millisecond. So the first instance of T2 would be completed by 4 millisecond. Now what happens at 4 millisecond? At this point of time, the first instance of T3 is available as well as the second instance of T1 is available. Alright, see, T1 arrives, the second instance of T1 arrives at 4 millisecond, but since T1 has the higher priority than T3, therefore we'll schedule T1 now. So we schedule T1. The second instance of T1 again completes in 1 millisecond. That means at 5 millisecond it has completed. Now at 5 millisecond, what do we have? Which tasks do we have? T1 has arrived at 4 and now it is finished by 5 millisecond. T2 is, the second instance of T2 is not yet present. It will come at 8 millisecond, but we still have one instance of T3, which is the first instance of T3 in fact. So we start the first instance of T3 and schedule it 1 millisecond at a time. At 6 millisecond, no other process of higher priority is available. So we keep on executing T3. At 7 millisecond, we again see that the third instance of T1 has arrived. Now T3 will again be preempted and T1 would be scheduled, and T1 takes 1 millisecond to complete, so it will complete in this time. So here T1 required 1 millisecond, it completed. T2, the first instance of T2 required 2 milliseconds, so it also completed. The second instance of T1 required a single millisecond, this is also complete. But T3 takes 4 milliseconds to complete and it has only executed till 2 milliseconds. So there are remaining 2 milliseconds of the first instance of T3. So let's continue and see at what time T3 would be complete. Now at 8 millisecond we see that the second instance of T2 also arrives. Okay, so since T2, the priority of T2 is higher than the priority of the remaining portion of T3, therefore we schedule T2, and we know that T2 has to complete in 2 milliseconds, or it takes 2 milliseconds to complete. Therefore we'll keep on executing T2 to its entirety, because there is no higher priority process, that is, there is no higher priority task present right now. So T2 executes for 2 milliseconds till time period 10. Okay, now what happens at time period 10, T2 is complete and T3 tries to take the execution, but again the fourth instance of T1 arrives at this point. Okay, at this point we have T1 as well as the remaining portion of the first instance of T3. Okay, so since T1 has higher priority, so we'll schedule T1 here. T1 only requires a single millisecond to complete, so it will complete by 11 millisecond. Now at 11 millisecond, what processes do we have? Only the remaining 2 seconds of 2 milliseconds of T3 are there, because we neither have the any instance of T2. T2 would now next arrive at 15 and T1 would next arrive at 13. Okay, so we can execute the remaining 2 seconds of T3 till 13. So T3 completes at 13. Therefore, what would be the answer in this case? The first instance of T3 completes its execution at the end of 12 milliseconds, because 12 milliseconds started at this point and 12 milliseconds ended at this point. Therefore, T3 completed its execution at 12 milliseconds. I would request the students to be very careful in such questions, because sometimes what happens that they correctly calculate this answer but still write the answer as 13. So please read the question very carefully. It's asking at the end of dash millisecond. Therefore, the answer would be 12. So that's all for today's lecture. If you understood this video, please mention in the comment section below. Like this video and share it with your friends, and let us know if you require more such tutorials in our preparation series. Thank you for watching. Stay tuned. Good luck.